go ahead and get started for today. I'm going to go ahead and throw up a little do now for you guys to work on. You can do this on a scrap sheet of paper or on the back of something. I don't really care. Share screen 2. There we go. Okay. So for the do now, on a scrap piece of paper, I'd like you to draw the Bohr model and the Lewis dot structure for sodium. Okay. So both the Bohr model and the Lewis dot structure for sodium side by side. So I'm going to give you guys about 5 minutes to go ahead and get that done, and then we'll go over it together. All right, how you guys doing? You good to move on? Want to go over this, or you need more time? Yes, no, maybe so. More time, or we're good to go?
I'm fine.
Peyton's good. Mackenzie, have you gotten a chance to do this yet?
Yeah.
Okay. So I'm gonna share a little whiteboard thing. Okay. So we can hopefully draw this a little bit easier. All right. So first, I'm gonna start off with the Bohr model. Okay. There is my nucleus. I'm gonna do it the text way because it's just a little bit easier in this program. So we got 2 recordings to put in the nucleus. We got the number of protons. So how many protons does sodium have?
11.
11, very good. And then I need to calculate how many neutrons sodium has. 22.9 is going to round up to 23, and 23 minus 11 gives us 12 neutrons. Okay. And now I need to draw my first electron shell. Move that out a little bit. There we go. And how many electrons can that first shell hold?
2.
2. All right, so 1, 2. I need to draw my second electron shell. Rearrange that, there we go. And that shell can hold how many?
8.
Correct, 8. Draw 8 real quick. 1, 2, 3, 4, 5, 6, 7, and 8. Please don't judge my electrons. Okay, and it has a total of how many? Total of 11, correct? And I have 2 on the inside, 8 on the outside, so that's a total of 10. So I need one more circle, one more shell. And in that shell, there's just a single electron left. Okay. So it's a somewhat messy but good Bohr model for sodium. Now, the next thing I need to do is I need to do the Lewis dot structure. So for this, I just write the chemical formula, which is Na. And around that chemical formula, I need to put how many dots? How many valence electrons does sodium have?
1.
1. So I'm just going to put one little dot right there. That's all I need for the Lewis dot structure. So again, if we look at these, there's, again, pros and cons, good and bad, of looking at both of these. Right, the Bohr model, the one over on the left, shows us the whole structure, tells us the atomic mass, tells us all the information that we need about the atom. And it also does tell us how many valence electrons it has, right? Because that electron there is the valence electron. But if I'm just doing how atoms bond together, I don't necessarily need to know all the interior stuff about the atom. I just need to know how many electrons are in its outer shell, and hence I have the Lewis dot structure or Lewis dot diagram with the single dot showing the same thing. All right, that this has one valence electron. All right. Are there any questions about how to make those models? Today, we're going to be mostly focused on how to make the Lewis dot structures. We're going to be using them a lot more today than the Bohr models, but I'm going to leave this up. We're going to come back to this as we go through the lesson today, because we're going to see how atoms bond together and how these bonds are going to change the atoms for good. Okay? So let's go back to the PowerPoint. All right, and now we're going to begin with the notes. So there are 3 different types of bonding. There are ionic bonds. There's something that we're going to talk about tomorrow called covalent bonds. And then one that we're not really going to focus too much on called metallic bonds. But these are the 3 main bonding types of atoms. So in ionic bonds, remember, everyone wants to get to 8 electrons in their outer shell. And if you don't have 8, you need to do things or react in a way that's going to lead you closer to that magical 8 number. So one of the ways that you can do that is by transferring electrons. So ionic bonds is going to be the gaining or losing of electrons in order to become more stable. So again, we're talking mostly about valence electrons. Remember, valence electrons are electrons that are in the outer or highest occupied energy level, the outer shell. And valence electrons are the only electrons generally involved in bond formation. So this is going to determine a lot of the properties of the element. How reactive is it? Is it very reactive? Is it explosive? Is it not very reactive at all? That can all be figured out by looking at how many valence electrons it has. So things get really reactive if they are really, really close to 8 or really, really far away from 8. So elements that are in the middle tend to be a little bit less reactive. They're not as dangerous, but ones that are really close to either like having 8, like 7 is really close to 8, or 1 is really far away from 8, those are going to be the most reactive elements because they are so close to having a full outer shell. So here is, again, our Bohr model of sodium. Okay, I can see the 11 protons and 12 neutrons in the center with 11 total electrons on the outside. So which one of these is the valence electron? It's that one at the very, very top in the outermost shell. And that's going to be the reason that sodium is so incredibly reactive. Now, here's the quandary that sodium finds itself in. It needs to get to 8 electrons in its outer shell. It only has 1 electron in its outer shell currently. So if it were to try and gain electrons, it would have to gain 7 electrons in order to get to that magical 8 number. Now, here's the problem with that. As I gain more electrons, so let's say I added another electron in here, that's going to now make there be 12 negative parts to only 11 positive parts. So what that is going to do is that's going to change the charge of this atom. It's no longer going to be neutral. Right now it's neutral because there's 11 electrons and 11 protons. But as these numbers start to change, the atom is not going to stay neutral. It's going to gain a charge. So if I add 1 electron, it's going to have a -1 charge. If I add 2 electrons, it's going to have a -2 charge. If I add 3, it's going to have a -3 charge. But here's the problem. Every time I add an electron, it becomes more negative. And what I'm trying to do is I'm trying to add a negative part, the electron, to a negative atom. And we know that like forces repel each other. They push each other apart. So it becomes harder and harder and harder to gain more electrons. So obviously sodium is not going to be able to gain enough electrons to become stable. It cannot gain 7 electrons. So what's its next best option? Well, what happens if I get rid of its 1 valence electron? Well, if I do that, now that outer shell is empty, it disappears. Now let's look at the shell right beneath it. 1, 2, 3, 4, 5, 6, 7, 8. So sodium, instead of trying to gain 7 electrons, is just going to get rid of 1 electron because the next shell underneath it is already full. It already has that magical 8 electrons underneath. So it becomes stable. So if sodium can find a way to get rid of 1 electron, it doesn't care who takes it. Just please take this electron so I can be stable. Now it's got a full outer shell, but look what happened to its charge. It became positive. Why did it become positive? Well, now if I count, there are 11 protons in the core, but there are only 10 electrons around the outside. So because there's 1 more positive than there are negatives, it gets the +1 charge. There is a 1 there. Chemists are lazy, so if it's a 1, they're not going to write it. If it's more than 1, you'll see a number there. But if you just see a symbol, just understand that means +1. You're going to find chemists are lazy a lot, but that's okay. Okay. This is also why my joke yesterday, I believe I told this one to this class, was hilarious. You know, one atom looks at the other atom and goes, dude, I think I lost an electron. And the second one goes, are you positive? Get it? Because it's positive charge. Haha. I know you're laughing. You're muted. I can't hear you, but I know in your heart you're laughing. Okay. Don't worry, guys. I'll only tell chemistry jokes periodically. Again, I know you're laughing. I know you're laughing. Okay, we'll move on. All right. So here's the question. When sodium loses its valence electron, what element does it look like? So we have a couple options here, but let's go back and look at here. Look at your periodic table. What element has 10 total electrons? Look at your periodic table. What element has 10 total electrons? If you're still laughing from my joke, I understand, but
Neon.
Ah, there we go. Thank you, Peyton. It's neon. What do we know about neon? What kind of element is neon? What's that last row called?
Noble gas.
It's a noble gas. So wait a minute. Noble gases, they're stable, aren't they? They're stable because they already have a full outer shell. So what does sodium look like when it loses that electron? Well, it looks like neon. Okay, it looks like neon, which is a noble gas. So what we're seeing here is elements are going to gain or lose electrons So they become like one of the noble gases. Everyone wants to be stable. Everyone wants to be like a noble gas. So they're going to react in a way that leads them to become more stable. Now, when an atom gets a charge, we no longer call it an atom. It gets a special name. It's called an ion. So we're going to see that if you lose electrons, you become positive. And a positive ion is called a cation. Okay? Think of that T. That T is a positive sign. That's a good way to remember cation. Cations are positive. Okay? T plus, cation, positive. So a cation is an atom that has lost one or more electrons and now has a positive charge. That's what happens to sodium. Sodium will now be called cation. Okay. Now remember, we're going to be using Lewis dot diagrams to show this bonding because this allows me to see how many electrons it have in its outer shell, how many does it need to become complete, how many does it need to become stable. So for example, if we look at chlorine, chlorine is in row 17 and it has 7 electrons in its outer shell. This is why chlorine is such a poisonous gas. This is why chlorine is so reactive. How many does it need to be stable? Just 1. It doesn't care where it gets it from. It just needs that 1 electron and then boom, it becomes stable. It's happy. Okay. Carbon is interesting because carbon has 4 unpaired sides. Chlorine only has 1, so it can only bond with one thing. But carbon is very, very versatile because it can make so many different bonds. And we're going to talk about the different kinds of bonds carbon can make as we get more into tomorrow's lesson. But carbon is very special because it's so versatile. Now, if we look at a shortened view of the periodic table, this is just showing us the Lewis dot diagrams for each column. Remember, group 1 has 1 valence electron. They all have 1 dot. Group 2 has 2, 3 has 3, or 13 has 3, 14, 4, 15, 5, all the way up until 18, which has 8, with the exception of helium. Because remember, helium is full with only 2 electrons. Because that first shell is full with only 2 electrons. So now hopefully you can start to see why the alkali metals often bond with the halogens. Here we have sodium. Sodium has 1 electron. Over here we have chlorine. Chlorine has 7 electrons. This is a match made in heaven. Sodium wants to get rid of that 1 electron. Chlorine is looking for just 1 electron. And so this is why sodium chloride is such a common thing. And sodium chloride, the common name for that is table salt. Okay? We take an explosive metal and a poisonous gas, and by transferring 1 little electron, it makes something so stable and so safe that we put it on all of our food. Okay? Or you should put it on your food, but not too much because that gives you high blood pressure and stuff like that. But please salt your food because that brings out more taste. Didn't think I was going to talk about cooking today, did you? Okay. Now, obviously, some of these are going to lose, right? So group 1 is going to lose. Group 2 is probably going to lose. Group 3 is probably going to lose because it's still easier to lose 3 than it is to gain 5. Now, group 14 is a little bit different because this can kind of go either way. I'll tell you, these don't often form ionic bonds because they're right smack in the middle. They're going to form a different kind of bond most of the time, and we'll talk about that one tomorrow, but they can form ionic bonds. So it's important to understand that is possible. Now, once we get to group 15, they have 5. So they're not going to lose 5. It's actually easier to gain 3. So these guys are looking to gain 3. Group 16 has 6. So they're looking to gain 2. Group 17 just needs that 1 because they already have 7. So they're looking to gain 1. And group 18 is not reactive because they already have a full outer shell. Guys, did you hear about oxygen and magnesium, the fact that they're dating? I was like, OMG. Get it? OMG. Okay. Again, I know you're laughing on the inside. All right. Trying to add a little humor today. All right. Now, obviously, if some lose electrons, they become positive. That's a cation. if some are going to be gaining electrons, they're also going to get a charge because they're gaining extra negative parts. And so they become negative charge. We call the negative ones anions because an is a negative modifier. So anions are negative ions, ones that have gained one or more electrons and are now negatively charged. So our example that we were going over was with chlorine. Here is chlorine in its natural state. It has 7 valence electrons. It needs 1. So when it gains that 1 electron, you can see that as added in right there, it gets an overall -1 charge. This is because it has 1 more negative part than it does positive parts at this point. So therefore, it has a -1 charge. If it gains 2, not chlorine, but if it, let's say oxygen only has 6, so it needs to gain 2. If it gains 2 electrons, it'll have a -2 charge. If it gains 3 electrons, -3 charge, so on and so forth. Now, when the valence shell is full, the atom is stable, and it's a whole lot less likely to react. The only ones to start off with that, like we talked about, are the noble gases, and that's why we call them inert. They are not reactive. They already have everything they need, so they're good to go. So what's important to understand is, again, atoms are going to tend to react in a way that's going to lead them to become more stable. Atoms are not usually going to react in a way that's going to make them less stable. So let's say, for example, I had magnesium. I'm going to draw this on the thing, so don't, you know. So here's magnesium. Magnesium has 2 electrons. And let's say we have chlorine. Chlorine has 7. Okay, so chlorine is looking for 1, and magnesium is looking to get rid of 2. These 2 are not going to bond together because even if magnesium gives away its 1 electron to the chlorine, it leaves magnesium with 1 electron in its outer shell. That does not make it happy. That makes magnesium very sad. Okay, so magnesium is not going to react with chlorine that much, at least if it's just 1 chlorine. Now, if there were 2 chlorines, well, that would give the other electron somewhere to go, wouldn't it? And that can happen if there's 2 and then 1 electron gets transferred to 1 chlorine and the other electron gets transferred to the other chlorine. Well, then all of a sudden, then magnesium might react this way. Again, because it's reacting in a way that makes it more stable. If it gets rid of both of these, it doesn't matter if it goes to 1 atom or 2 atoms. If it gets rid of both of them, then it becomes happy. So again, this is just to show that atoms are going to tend to react in a way that makes them more stable. Okay, so if it was just the magnesium and 1 chlorine, it's not going to work because that would leave that leftover valence electron. But if we double the amount of chlorine that we're adding, all of a sudden now this starts making sense. All right, so what this slide is showing is the formation of a cation. This is just an easy way to think about the equation. Hydrogen has 1 valence electron. Therefore, it's looking to get rid of that 1 valence electron. And when it does that, it becomes positive. So this is showing, I do not, sorry. This is showing us sorry, someone just walked in and threw my train of thought off. So again, hydrogen is going to become positive, all right, when it loses that 1 electron. Now notice down here magnesium. Now this is a bad Lewis dot structure. It just has to do with the way the formatting works. We know that this should not be here, but it should actually be somewhere else on another side, okay? So just understand that that's not quite correct, but we can see here, magnesium has 2 valence electrons. It needs to get rid of 2 electrons. And what happened to its charge when it got rid of 2? Well, it got a +2 charge, okay? So again, chemists are lazy. Lithium has a +1, hydrogen has a +1. If you want to put +1, that's fine with me. I'm okay with that. But if you see this is not lit. This is lithium +1, okay? This is showing the formation of anions. Remember fluorine is in group 17 as well. It has 7 valence electrons, so therefore it just needs 1 valence electron to make it happy. So that one's going to join the party. And when that happened, fluorine got that negative charge because now there's 1 more negative part than there are positive parts. Now, when these things form, they actually get a name, okay? Because we don't call salt sodium chlorine, we call it sodium chloride. So the name is going to change a little bit when it forms an ionic bond. Now, the metal is the cation. If you look at the left side of the table, look at the left side of your periodic table. What color are all of those atoms? If you're looking at your periodic table on the left side, what's the majority of atoms? What's that color?
Blue.
They're blue. And blue means that they are metals. Now remember, the ones on the left side are looking to get rid of their electrons. Okay, so metals are good at giving away electrons. That's why they're going to form the cations. So when sodium loses its electron, it's no longer sodium. We call it a sodium ion. Okay, a sodium ion. This is very simple. So sodium, you just take the name of the metal, you smack on an ion. Okay, it's not going to be same for anions. We'll see that in a moment. But sodium is going to keep its name. It's just going to become a sodium ion. So, for example, potassium is the same way. Potassium is going to lose an electron. Therefore, it's going to become a potassium ion. Anions are a little bit different. For anions, you drop the ending of the non-metal, right? Because the ones that are gaining on the right side of the table, if you look at that, those are, I think, yellow, right? Maybe? Can't remember what color it is on your periodic table. But it's the color that shows that they are all non-metals. So you're going to take the non-metal, you're going to drop the ending, and you're going to add IDE. So fluorine becomes fluoride. Chlorine becomes chloride. Bromine becomes bromide. Okay, so you drop the ending and you add IDE onto the end of it. So, ionic compounds, these are a joined ionic bond, are made up of a metal and a non-metal. Okay, metal and a non-metal. So, for example, if we added sodium and fluorine, sodium is my metal, fluorine is my non-metal. Sodium has 1 valence electron, fluorine has 7. So this can form an ionic bond, and it becomes sodium fluoride. Keep the name of the metal, and then you change the ending of the non-metal to IDE. We could also talk about this with sodium and chlorine, right? Sodium and chlorine becomes sodium chloride. Same idea. So the key here is an ionic bond needs to be between a metal and a non-metal. So we take a look at this one just real quick. Here we have sodium, that's a metal, chlorine, that's a non-metal. Is this going to be ionic bond? Yes, it is. But what about number 2? We've got carbon and we've got oxygen. Is that going to form an ionic bond? Is that a metal and a non-metal? Go ahead and peek at your periodic table. Is that a metal and a non-metal? Is carbon a metal? Someone looks like, Peyton, it looks like you're talking, but I can't hear you. Nope, carbon is a non-metal.
No.
Is oxygen a metal?
No.
No. So this is 2 non-metals. So this is not going to form an ionic bond. Again, we have carbon monoxide, not going to form an ionic bond. What about potassium and fluorine? Is potassium a metal? Look all the way on the left of your periodic table. Is potassium a metal?
Yeah.
Okay. Is fluorine a metal? Or is fluorine a non-metal? All the way on the right side of your table. It's a non-metal. So this can form an ionic bond. And here we have more than two, right? But I have a metal and non-metals. So that could also form an ionic bond. Has to be between a metal and a non-metal. Okay. Now, elements that do not have a stable octet tend to react. And when the elements react, bonds will be formed. So the question that we have to ask ourselves is, how is this bond being held together? So in ionic bonds, again, there's a transfer of electrons. Transfer, it's giving it away. One is giving it away, the metal is giving it away, the non-metal is taking it in. There's a transfer of electrons from one element to another. Now each element, which now has a charge, it's now an ion, each element will have a stable or complete octet after the transfer. That's key. Again, they're not going to move in a way that's not going to lead them to become more stable, to become less stable. They're only going to react in a way that makes them more stable. Now, what holds these together? If I give something away, if I give away an electron, will I become positive? As the other element gains an electron, it becomes negative. Guys, what do we know about opposite charges?
They repel each other. Wait, what?
Well, if it's the same charge, they repel each other. But if they're opposite charges,
Oh, they bond, like they come
yeah,
together.
they attract one another. Okay. So what holds ionic bond together is the electrical force between the two different ions. This positively charged sodium and this negatively charged fluorine. Those charges are going to cause it to stick like magnets. So sodium and fluorine are now going to be stuck together because of their charges. Okay. Lithium is going to work the same way. Here's lithium and fluorine. Lithium fluoride. Lithium has 1, fluorine has 7. Lithium is going to transfer that 1 electron to the fluorine. And now lithium becomes lit, just kidding, Li plus, right? That becomes positive. The fluorine becomes the worst grade, F minus. No, just kidding. It becomes negative. Shouldn't joke about this. And we get lithium fluoride. This positive charge is going to attract that negative charge, and that's why these two stick together. All right. Now, sometimes we're going to need to record these with a chemical formula. So let's talk quickly about what a chemical formula is. A chemical formula represents the kinds and number of atoms in a substance. You guys have already dealt with chemical formulas. You don't even know it. What's the chemical formula for water?
H2O.
Bingo, look at that. You know chemical formulas, look at that. H2O. So if I look at H2O, oops, that's not what I wanted to do. There we go. All right, H2O. That means that there are 2 hydrogens. That's what that little 2 means. And there is 1 oxygen. Remember I told you chemists are lazy, right? They're not going to include a letter if there's not at least 1. And if it's more than 1, they have to put a number. So if you don't see a number there, what's the number? It's just the number 1. So H2O is the chemical formula for water. There's 2 hydrogens for 1 oxygen. Now it's important to understand the chemical formula shows the lowest whole number ratio. So for example, if I had H4O2, that's not technically correct, all right? Because what do I know about 4 and 2? It's like fractions, we can reduce it, right? Is there a number that goes into both 4 and 2? Well, of course,
2.
It's 2. So if we reduce that, it's now going to be H2O1, okay? So it does need to be in the lowest possible ratio. That's not going to be super important until maybe later this week, probably more likely next week when we start balancing chemical equations. But just understand it does need to be the lowest possible ratio. All right, God, Nick, shut up. You've been talking all class. Can we please just get a break from your voice? Almost. So all we have left for today are the practices. I don't expect you to get done all the practice that I gave you. We're gonna continue working on this some tomorrow. Let me go ahead and share my screen. Okay. So we are again working in day 15 at ionic bonds. If I click here, you do have the practices, but I gave you guys paper copies. Now on this one, all right, this is, I believe, the very next page on your notes. Is that correct?
Yes.
All right. Do me a favor. You see this big fill in the blank part at the top? You can go ahead and cross that out. We are not going to do that. That is not an editable document for me, unfortunately, so I can't change that. But this chart at the bottom is phenomenal. I love this chart because what this is going to help us with is seeing where the elements are and what do they need to become stable. Okay, so cross out the very top, but let's go over a couple of these on the middle, on this chart. So we can go over some examples. Now, I'm not going to be able to type in this, so you're just going to have to bear with me and follow along. So for sodium, how many valence electrons did sodium have? It had 1 valence electron, right? So what is it going to do? Is it going to gain 7 or is it going to lose 1? Maybe I can edit this. I don't think I want to, but maybe I can. Let's try it. I think it goes haywire, but I can't remember. Hey, look at that. All right, so sodium had 1 valence electron. So what's it going to do? Is it going to gain 7 or lose 1?
Lose 1.
It's going to lose 1. So I write lose 1. And then this says this oxidation number. That just means after it changes, what charge is it going to have? So if it loses 1, what's its overall charge going to be? Loses 1 electron, so it becomes
Positive.
+1. So I'm going to put a +1 there. Okay. Let's jump down to, let's do oxygen. How many valence electrons does oxygen have?
6.
It has 6 valence electrons. Very good. So is it going to lose 6 or gain 2? Which is easier, losing 6 or gaining 2?
Gaining 2.
Gain 2. Right. And when it gains 2 electrons, what's its overall charge now?
-2.
It is -2 because each time I gain an electron, it's another negative charge. So if I gain 2 electrons, I get a -2 charge. So I then have 2 more negative parts than I do positive parts. You guys have any questions on this first chart thing? This is really good to think about atoms and what they need to do. All right. Then we're going to get into diagramming, and this is where it really gets messed up. If you guys turn the page over, yours is separated a lot better than mine is showing up here. But let me do this. I'm going to switch over to the camera because I want these diagrammed in a very specific way. And this is not meant to be a pain in the butt. This is meant to help you guys learn this and make a whole lot less mistakes. So let me plug in the camera real quick. I can do this on paper. You can see it. Stop share. Go to the camera, please. Start the videos. There we go. I don't know if I can, let's see, do the hard zoom. All right, you guys can see sodium and chlorine there?
Yeah.
All right. So what you have to do first is you have to draw the Lewis dot diagram for each of the elements. So for sodium, I'm going to write Na because that's the chemical symbol. It It has one valence electron, so I'm going to put one dot to it. Then I'm going to put a plus sign. Then I'm going to draw chlorine's Lewis dot structure, chemical symbol Cl, and I know that chlorine has 7 valence electrons. Then what I want to see is I want to see an arrow. So you're going to draw an arrow for each transfer. Now this one only has one, so I'm only going to draw one arrow. But I want to see that sodium is giving away its electron to the chlorine. Then you're going to draw an arrow like this. This is an equal sign in chemistry, okay? This arrow means yields, okay? So that means that chemical change is occurring. So it yields something. Now I'm going to run out of room because I'm trying to write it big so you guys can see it. But now what you need to do is you need to draw the formed compound. So I still have sodium, but now it has no dots around it, right? Because it gave away its valence electron. So what charge did it get when it lost its electron? If I lose an electron, I become
Positive.
Positive.
positive. Good. So I put a plus sign there. And then right next to it, I draw chlorine, and chlorine now has 8 dots because it gained that extra electron. And now because it gained 1 electron, it has a charge of -1. Okay, so this shows me the formed compound. Guys, another clue is that one of your elements should have no dots around it, and the other one should have all the dots around it. That means that you did it right. If you end up with one that has one left over, you did something wrong. Okay, I do want to go over a few more just real quick. Let's take a look at number 3. Jump down to magnesium and oxygen. OMG. Oh, sorry, I didn't finish this one. I'm sorry. I'm getting ahead of myself because I like just joking about that. So now what's the chemical formula? Well, how many sodiums did it take to make chlorine happy? It took 1 sodium and 1 chlorine. So my formula is just NaCl. 1 to 1. If it took more than 1, we'd have to put a little number in here, but this one was just a nice, easy 1 to 1. And now I need to name it. I use the name of the metal, so that's sodium. Okay, and then I change the name of the non-metal, take off the N, and put IDE, right? Sodium chloride. All right, now that one's done. Now let's go down to number 3. So for number 3, I have magnesium. Magnesium's chemical symbol is Mg. It is in group 2, so that means it has 2 valence electrons. Okay, I'm going to add that to my oxygen, which is in group 16. So that means it has 6 valence electrons. So what's going to happen here? Well, magnesium has 2 that it's looking to get rid of. Oxygen needs 2. It's a match made in heaven. OMG. Sorry, that'll be the last time. So magnesium is going to give 2 electrons. So I want to see 2 arrows there showing the double transfer. Then we draw our yield sign. Okay. Now I write magnesium. Magnesium lost 2 electrons. So what is its charge? It lost 2 electrons. It has a charge of
Positive.
positive how many? You're right. Positive
0.
If it lost 2 electrons, got rid of 2 negative parts, it's going to have a +2 charge. Because now it's double as positive. It lost more than 1. So it lost 2 electrons. And then I'm going to draw oxygen now with 8 dots around it because it gained those 2 electrons. So what charge does it have? It has a -2 charge. So another way to see this, guys, is look, my charges should also cancel out, right? I've got a +2 and a -2. Your charges should cancel out to become 0. This top one, I had a +1 and a -1. Your charges should still cancel because overall charge should remain neutral. We're going to do one more together. I'm going to set you guys loose. So for number 5, we have calcium and we have chlorine. So calcium, oops, sorry, I'm getting ahead of myself. We need to do a formula name for this one. So the formula is MgO because it's just 1 to 1. The name is magnesium oxide. Magnesium oxide. Name of the metal you keep, name of the non-metal you change the ending to IDE. All right, now on number 5. We got calcium and we got chlorine. If I can get the camera. Calcium's chemical symbol is Ca. It is in group 2, so I know it has 2 valence electrons. I'm going to add that to chlorine. Chlorine is group 17. So therefore it has 7 valence electrons. What's the problem here? There's a problem that you can hopefully see right away. What's the problem here?
There's too many electrons.
Yeah. Can chlorine take in 2 of calcium's electrons? No, it cannot. Chlorine only has room for 1. It already has 7. So how do I fix this? Well, I need to get rid of 1 more electron. So what I'm going to do is I'm going to give it somewhere to go. I'm just going to simply add another chlorine atom. Now look at this. The first electron can transfer to this atom. The second electron can then transfer to the second atom. So if your numbers don't match up, just add in atoms until it makes everyone happy. Now this one's going to be a little bit different in what it looks like at the next part. So I'm going to draw my little arrow. I'm going to do it underneath so I have a little bit of room. Okay. So now I'm going to draw calcium in the middle. Calcium lost 2 electrons, so it has a +2 charge. I'm going to draw chlorine on one side with 8 dots, and a chlorine on the other side with 8 dots. And the reason that I'm spraying the chlorines out is because they have what charge? Well, they each gained 1 electron. This is what makes this tricky. This chlorine only gained 1 electron, so it has a -1 charge. This chlorine only gained 1 electron, so it has a -1 charge. So let's see if my charges still cancel out. I've got -1 and -1, so that's -2, and I've got a +2. So it does in this case cancel out, and that's how I know that I did this correctly. Your charges should always cancel each other out. It's your last check. Calcium had no dots around it because it gave its electrons away. Each chlorine now has a full stable octet, so this is one happy compound. Now, if you notice, this chemical formula is going to be a little bit different. There's still only 1 calcium, so I'm going to put Ca, but then I'm going to put Cl, and how many chlorines did it take to make calcium happy? It took 2, so I'm going to put Cl2, okay? The name doesn't change. I still use the name of the metal, which is calcium. And then I change chlorine to chloride. Okay, what questions do you guys have about that one? All right, here's what I would like for you to do, okay? You got 2, 4, and 6. Sorry, let me zoom this out so you can see, okay? You've got number 2, number 4, and number 6 to complete on this one. And don't forget to flip back and complete this table, okay? Complete the table, and then the even problems that we didn't go over on the back, let's go ahead and let's save ionic bonding worksheet for tomorrow. Don't work on this one yet. We'll do this one tomorrow. Okay, so just finishing the chart and then finishing those 3 problems that we didn't go over. Okay, and then if you do look in the class, there is an, actually I gave it to you guys. On the very last page of this, there is an exit ticket. I think I also put it online. So I don't care where you do it, but this is the exit ticket I would like you to complete. Okay, so I will be collecting the exit ticket and I'll be checking your practice tomorrow as well. Don't do the middle worksheet, okay? Don't do this one. Let's save this one for tomorrow. Okay, just finish this page that we were working on, front and back, and then do the exit ticket. Okay. Do you guys have any questions for me? All right, I will take that as a no. So you guys have your assignment, finish up that 1 page front and back, and then complete the exit ticket. And I'll be collecting the exit ticket to start a class tomorrow. All right, I am going to close out so this can convert and I can post it later. You guys feel free to head out, complete that work. I will see you tomorrow in class. Thank you so much for Zooming with me today.